Okay, in this lecture we will continue with single transistor amplifiers. Up to now we have seen the MOSFET amplifier types. As you may remember, for common source we also have common source with degeneration. So this one is a good voltage amplifier. This one is a good voltage amplifier as well, but the voltage gain is a bit smaller than common source amplifier. However, it has some other advantages like high output resistance and much more stability, transistor independent performance, and so on and so forth. For common drain, we said that it's a good voltage buffer with low output resistance. Input resistance is still high, but the gain is like almost 1. So let's write these very quickly. Common source and common source with degeneration are in, are out, large, AV, large. Of course, with degeneration, AV decreases a bit. For common drain, gain is less than 1, but with a good design, you can make it like 1. Rin is large, R out, low. For common gate, so this is like a good voltage buffer. And for common drain, so for common gate, Rin is very low. And because of that, you cannot use it like a voltage amplifier, even though the expression is quite similar to common source one. R out is large, and it's a good current buffer. So we have completed the discussion on MOSFET amplifiers. Now we will focus on bipolar transistor amplifiers. In fact, they are quite similar, but the main difference is base current of bipolar transistor is not equal to 0, and because of that, it will bring some differences in small signal analysis. The input resistances will be different. So let's start work on them. Let's start with common emitter amplifier. For the common emitter amplifier, let's draw a typical one. Let's use an ideal current source first, like we did in common source amplifier, to be consistent, but you can replace it with a resistor. Or let's make it like this, sorry. Let's replace this with 2 resistors. To be consistent, let's make this as R3. So this is a typical common emitter amplifier. As I drew previously, my previous drawing was also correct. You can replace this part with ideal current source. It's not going to change the result. But in here, I want to show you 2 cases together. If you have R50, this is known as common emitter. Why? Because then this part is shorted. This node is AC wise grounded. It's a common emitter amplifier. Remember the node names collector, base, and emitter. When R5 is equal to 0, you have short circuit. This is a bypass capacitor. Emitter is shorted. We have common emitter amplifier. If R5 is not equal to 0, then it's known as common emitter with degeneration. It's quite similar to common source and common source with degeneration. I'm going to change these notations as well. Let's say this is C3, this is C2. C1 and C3 are isolation capacitors. Like in the MOSFET case, they isolate DC from AC or vice versa. C2 is bypass capacitor. The first thing that you should do is, of course, again, it will be DC analysis, to ensure proper operation region, and to find small signal parameters, and then we will have small signal analysis. But of course, the proper operation region should be redefined. Small signal parameters should be redefined. They are not the same as MOSFET case, so we have to remember operation region and small signal parameters. Okay, we have to remember them. So let's review the BJT basics first. We will do it. But like in the previous MOSFET case, I found a very nice video on YouTube which explains the bipolar transistor operation in 5 minutes in principle. So please check the website. I'm gonna give the link in auto class as well for this website so that you can watch the video. Please watch it and try to refresh your memories from 212 on bipolar transistor working operations. But please keep in mind that this course is different than 212. We do not worry about the physical phenomena behind that much. What we care is like we assume that we want to take this transistor as a black box, and we are trying to find the mathematical relations between input and output for DC and AC. So these are like mathematical boxes for us. Physical things happening inside are not that critical, but they are useful to understand that mathematical formulas. So let's remember them very briefly. So you see a bipolar transistor structure in here. What you have is in fact two back-to-back connected diodes. You have two back-to-back connected diodes. And unlike the MOSFET, this structure is not symmetrical. This is not symmetrical. For MOSFET, during the circuit operation, that doesn't matter whether you connect source or drain to some port. Depending on the current directions and the voltage biasing, source and drain may exchange. None of the ports are specified as source or drain. Source and drain are defined by the circuit operation. But for bipolar transistor, it makes a difference. This highly doped part should always be emitter. For MOSFET, we have two types, NPN or PNP. For NPN, for all the time, of course, emitter current is always equal to base current plus collector current. So what you do in here is, like, for this NPN structure, for example, you are, forward. You are trying to bias this PN junction in forward active region, and this, the other diode in here provides some carriers to enhance the current passing through the other diode, or vice versa, depending on the operation type. When you compare NPN and PNP, the main difference is base current and collector current are negative, so the actual directions are like this. So this is for NPN transistor. Base and collector currents are going towards the device. Emitter current is flowing outwards. But for PNP, emitter current is going inwards, and base and collector are going in the other direction. The operation curves are quite similar to MOSFET. Assume that we are changing VCE, and assume that emitter is grounded. We have some base voltage defined as VBE. We have two important curves. One of them is IC versus VBE. The other one is IC versus VCE. Remember, for MOSFET it was ID VDS, ID VGS. They are the same, but the subscripts and the notations are changed. IC VBE is like the diode characteristic, exactly like the diode characteristic, something like this. IC VCE is something like this. So this is as I base is increasing, we have forward active region and saturation region. Keep in mind that for MOSFET, saturation was this part was called as linear, but now saturation is a different part. For bipolar transistor characteristic, forward active is a different part. So for forward active region, IC is equal to beta F I base. For saturation part, IC is less than beta F I base. So for bipolar transistor, in fact, you have again three operation regions. The first region is cutoff. In this case, both diodes are off. So assume that you have two diodes in here, one of them in this direction, like this one, the other one is like this one. Why? Because I have NPN, so this is emitter, collector, and base. So in this region, you have base emitter junction. Here you have base collector junction. So base collector diode is this one. Base emitter junction is this one. For cutoff, you bias collector, base, and emitter such that none of these diodes are on. Therefore, no current passes. ID, IB, IE, all of them are at 0. In the second region, which is, let's say, forward active, now base emitter junction is on, base emitter diode is on, base collector is off. So this diode is off, this diode is conducting. The current is passing through this diode. this one. In that case, what happens is IC can be given as beta F I base, and I emitter is equal to beta F plus 1 times I base. The basics of bipolar transistor operation is reviewed by Professor Kocaman in his own Q&A and recitation sessions, and they were uploaded on the ODTÜ class. So if you want to learn about more details in here, please watch the videos or take a look at the notes provided for bipolar transistor operation principles. But basically, as a mathematical model, I want to consider these three regions. So I'm not going into the details of the physical operation principle. And the last region is known as saturation. And in that case, both diodes are on. So forward active region of bipolar transistor corresponds to saturation region of MOSFET. So for analog operation, I want this bipolar transistor to be in this region. So this region is desired for analog operation. Of course, not all the time, but like 90% of the time, you prefer your transistor to be in this region. If it is not in this region, you cannot talk about small signal. So to be able to talk about small signal amplification, you want your bipolar transistor to be in forward active region. And in here, we assume that this line is parallel to x-axis, which is in fact not true in reality due to something like channel length modulation. So this early voltage thing is similar to channel length modulation in MOSFETs. So in the actual case, there is some non-zero slope in here, and this slope corresponds to 1 over R0 resistance. And they find it by using some experimental calculations. So each of these lines are crossing at minus VA point, where VA is the early voltage. And this early voltage is in the range of, like, let's say 100 to 200 volts, which means that it's a very large value compared to a typical biasing in bipolar transistor. And from here maybe you can find the slope if you know the, so slope can be calculated if you know the operation point. So if you know, let's say, VCEQ quiescent point, and if you know ICQ, then you can find the slope. In other words, you can find the output resistance of the bipolar transistor. I will discuss this thing later on, but just keep in mind, it's quite similar to MOSFET. So to summarize, cutoff, VBE is less than VBE on. Remember that this is the structure, collector, emitter, base. And imagine two diodes in here. One of them is base emitter junction, the other one is base collector junction. And this turn on voltage, something like 0.7 volts. For cutoff, VB is less than VBE on. And VBC is less than VBC on, which means that both diodes are off, and therefore IC is equal to I base, which is equal to I emitter, which is equal to 0. So the equivalent circuit is like this open circuit at all ends, collector, base, and emitter. Remember that this is a non-symmetric device. Emitter is a bit highly doped compared to collector. Therefore, turn-on voltage of base emitter junction and turn-on voltage of base collector junction are not the same. So in general, like you can think that like this is 0.5 volts, but in some examples they can be given as the same, so don't worry about it. But keep in mind that this is an asymmetric device, and because of that there is some small difference between turn-on potentials of base emitter and base collector. For saturation, both base collector junction and base emitter junctions are on, which means that VB is equal to VBE on, VBC is equal to VBC on. In this case, we have a large base current passing through the base of the transistor. And we have to make a correction in here. If you have large base current, which means that you have a bit large current passing through base collector and base emitter junctions. And let's remember the diode curve. Okay. So if this is the on voltage, let's say 0.7 volts, this is I versus VD, let's say ID versus VD. If your current level is a bit large, then you're operating somewhere in here. And assuming like 0.7 volt as the voltage across a diode is not realistic anymore. So if it is a diode, if I take like 0.7 volts, it's going to be a mistake, because for large ID currents, your turn-on voltage or voltage across a diode is a bit large. So instead of on, we generally use SAT terms in here, VBE SAT and VBC SAT. So this is something like 0.8 volts. This is something like 0.6 volts. And in this case, the only thing that I can say is I emitter is equal to I base and I collector current. That's number one, or the first equation. The other equation is IC is less than beta F I base. This is the second condition. And of course, since both of the diodes are on, we have, let's say, VB is set in here, VBC is set in here. To be able to satisfy the KCL and KVL, this voltage is VB set minus VBC set, which is VC set. VC set is equal to VB set minus VBC set. So we check these three equations for finding voltages and currents across the bipolar transistor. For forward active case, only base emitter is on, VBE is equal to VBE on, IC is equal to beta Fi base, IE is equal to, of course, IC plus I base. KCL should always be verified, which is beta F plus 1 I base. And what can you say about collector emitter voltage VCE? Of course, VC is larger than VCE set. So these are some expressions in here, but at the end of the day, what you are going to use for our case, this is the most important region for us. For small signal operation, far operation should be verified for BJTs. And how do you verify it? First, you are going to assume far operation. So set VBE is equal to VBE on. Set, so this is number one. This is so set IC is equal to beta F I base and IE is equal to beta F plus 1 I base. Then, third step, check VCE. If VCE is larger than VC set, far assumption is correct. Then go ahead with small signal analysis. So you can proceed to small signal analysis, and you can find the small signal parameters. If VC is less than or equal to VC set, transistor may be in linear, and stop the analysis. You cannot talk about small signal anymore. You should stop there. Either you are going to change the operation point such that your transistor is in forward active, or you are going to say that this is not an amplifier. I cannot find small signal parameters. When you are finding collector current in forward active, I mean, you can use this expression as well. IC is equal to ICS e to the power VB divided by VT minus 1. Collector current depends on base emitter voltage, of course, where IC is scale current or saturation current, whichever you call. VT is KT over Q. And in here, K is Boltzmann constant, T is temperature in Kelvin, Q is electron charge. So I should say temperature in Kelvin in here. So if you know VBE and operating temperature, of course you can write the collector current with this expression as well. But you know, we rarely use this thing. In fact, we said that the transistor has 3 operation regions, bipolar transistor, but in digital electronics course, you will see that there is another region which is called as reverse active region, where you replace collector and emitter. But for the scope of this course, we only consider these 3 operation regions. So let's continue with the analysis. For DC analysis, what you should do is, so I'm doing DC analysis on this page, and I am doing the same thing for both common emitter and common emitter with degeneration. The first thing, kill AC sources, and then short isolation and bypass capacitors. So what I do is, this is shorted, sorry, they are isolation and bypass capacitors should be opened. I'm correcting. So what I do is, short this one, open this one, open this one, and this one. And this circuit in here will be my DC equivalent circuit, which is shown in here. Okay, and you can further simplify it, like, you know, R5 or R6 are in series, so they are shown as a single resistor. We can do further simplification in here by using Thevenin equivalent. So this part can be given by this simplified part. And in this analysis, what I should show is, as I said, the first thing, assume, let's name it as Q. Q is in forward active region. Second, set VBE is equal to VBE on, which means that this is like 0.7 volts. The third thing is set IC is equal to I base times beta F. Now you can write a loop equation in here because you know this voltage, you know this voltage, you know the relation between I base and I emitter. I emitter current is beta F plus 1 I base, and you know the resistance values. So from here you should be able to find I base value. Okay. Now you can find I base, you can find I emitter, you can find I collector, which is good. And the last thing that you should do is check whether VC is larger than VC sat or not. If it is larger than VC sat, then your forward assumption is correct. You can continue with the small signal analysis. If not, stop there and don't do anything in terms of small signal analysis. So if this thing is verified, you can continue with small signal parameters. We have again two models. One of them is hybrid pi, the other one is T model. When you take a look at this hybrid pi model, the main difference from the MOSFET case is you have a finite resistance between base and emitter. For the MOSFET, this resistance was infinite. Why? Because gate current of the MOSFET was 0. But for bipolar transistor, base current is not equal to 0, and because of that, you have a finite resistance, which is given by this R-pi notation. The rest is quite similar, like this is like GM VGS, this is R0, you have VGS, but instead of infinite resistance, you have some finite resistance in here. So now, in this expression, we have to find three important parameters, small signal parameters, R-pi, GM, and R0. Let's start with GM and R0. You can continue with the definition, in fact. GM is defined as output current versus input voltage. Some current divided by voltage. Output current. Remember that a transistor is a transconductance. I can write better than this, I guess. Transconductance amplifier, which means that your output is IC or ID for MOSFET. Input is VGS or VBE for bipolar transistor. So I am taking a look at collector current versus VBE voltage. Since it is not linear, I am dealing with derivatives in here. So what I can do is del by del VBE times ICS exponential VBE divided by VT minus 1. And if you solve this, you will find it as IC divided by VT. Okay. For R0, again, we can continue with definition. By definition, this is the output resistance. It is voltage divided by current. Output voltage divided by output current. And it should be partial derivative. And if you assume that no early effect, so if we ignore early effect, R0 goes to infinity. So remember this drawing. Sorry for my bad drawing, but so this is the ideal case with no early effect. But if you take into account the early effect, you will see that there will be some non-zero slopes in here, and all these lines are crossing at here. And the slope in here is in fact 1 over R0. Okay? And if you know the operation point, let's say that this is my operation point, VCEQ and ICQ, you can find the slope as ICQ divided by VCEQ plus VA, the early voltage. But remember that early voltage is around like 100 and 200. But VCEQ is limited by the power supply of the circuit, which is at most, let's say, 12 volts. On IC, you can find it like even less than that. So this term is negligible compared to the early voltage. And because of that, you can write R0 as VA divided by IC or ICQ. Now I have two unknowns. One of them is RPi, and I need RE if I want to use the T model. Let's highlight it as well. We need to find it if I'm going to use T model. So GM is right now find. R0 is also known, and now I need to find RE and RPi. RPi. It is the input impedance, right? You are seeing it from the input, and it's the resistance. Therefore, it's going to be some voltage divided by current. Input voltage, input current, VBE, IB. It's not linear, so I'm going to use derivative. And if I use it, in forward active region, IB is equal to IC divided by beta. So it will be 1 over del IB divided by del VBE, which is beta over del IC by del VBE. This term, we already defined it in the previous slide, which was like GM, which was VT divided by, sorry, it was IC divided by VT. So the result will be beta times VT divided by IC. So our pi will be equal to VT divided by IB. So now I know our pi. For our emitter, you can do a similar calculation. Now it's like input voltage versus emitter current because it's appearing at the emitter. So the voltage is input, current is passing through the emitter. So by definition, you can write it as del VB divided by del IB. And if you make the same calculation, now, sorry, this should be I emitter. And in that case, 1 over del I emitter by del VB, which is like beta over beta plus 1 del IC by del VBE, and the final term will be VT divided by I emitter, which is small re. Well, I think you can follow these derivations, but if you have any difficulty in following these derivations, maybe you can use a short path, which I can show. So we have two terms, GM, R0, R pi, and RE. So what you can do is, GM is transconductance. It is current divided by voltage. Which current? GM is appearing at the collector, so it should be IC. IC divided by VT. VT is fixed for GM, R pi, and RE. R pi, some voltage divided by current. Which voltage? VT. Which current? It's appearing at the base, so you should divide it by I base. Similarly, R emitter, voltage. Voltage divided by current. Which voltage? VT is fixed. Which current? RE. As the name implies, it's at the emitter, so you should use VT divided by IE. For R0, it's voltage, V divided by I. Which voltage? Now that's the only difference, because you have a very high resistance. It's related with the early effect, so you use early voltage. R0 is appearing at the collector, so the current should be collector current. And in all of these expressions, Vt is equal to Kt over Q, which is 26 millivolts at 300 Kelvin. Va is early voltage. It's in the range of like 100 to 300. So now I know the small signal parameters of the bipolar transistor. I can use either hybrid pi or T model. So R pi is known, GM is known, R0 is known. In this case, R0 is known, GM is known, RE is known. So I am ready to continue with the small signal analysis, which I am going to do in the next lecture.